All right, let's do this. Welcome back, everybody. Welcome to day 3 of our Learn Java Live webinar. And today, day 3 is the fun stuff, in my opinion. We're going to dive into some data structures to help generally prep for the technical interview. These are the kind of things, for better or worse, a lot of interviewers like to see that you've got a good, strong grasp on at least the fundamental data structures and sorting algorithms. And so today we're going to look specifically at the linked list and the hash map. For those of you who are joining us for the first time, my name is Ryan. I'm a co-founder of Coding Nomads. I've been a Java engineer for a long time, and I've been teaching it for a long time as well. In this training, it's going to be all about data structures, right? And understanding what they are and why they're important. And a really important thing when it comes to these kind of what I call abstract data structures is how to think about them, right? Because they're a little bit different than, for instance, the array that we're comfortable using that we covered in day 1, or the array list. They're just a little bit different in that we think about them a little bit differently. And what we do is basically set up rules or controls for how we can add, remove, and find things in a collection of data. And the rules that we set up define the data structure. And this will make more sense shortly. So specifically today, we're going to discuss how to build a custom linked list. And then after we've built that, I'm going to give a quick nod to both the queue and the stack data structure because the linked list lends itself well to being the underlying data structure in in a queue or a stack. And then we're going to build a custom hash map. And the hash map has always been my favorite data structure. There's something about it that's just really nice and fast and simple and smart. And I really like it. And I think you will too. And we'll discuss that in just a little bit. So what is an abstract data structure? As I mentioned, an abstract data structure is simply an idea about how we store data and how we control access to that data. So for instance, if we look in this diagram here that we have to the left, oops, here's just, here's a quick diagram that I have of a stack data structure. And a stack is a very common data structure. You might recognize the name from Stack Overflow. All of our computers are using stacks as a data structure to store commands that they need to run in a specific order. And a stack data structure is quite intuitive because it's just like a stack of plates on the table. If you're going to take a plate, you're going to take a plate off the top of the stack. And if you're going to put a plate down on the stack, it's going to go on the top of the stack. So with a stack, we typically use the terms push to add something to a stack and pop to remove something from a stack. And with a stack, we can only push to the top of the list or the front of the list, and we can only pop from the front or top of the list. It's the only spot that's accessible. And back when I was a kid, we used to go to Sizzler sometimes. I remember the plates at the salad bar. They actually push down into the counter, right? So you can't actually see the whole stack. You can only access the top plate, right? And I think that's a really good visual or analogy for how a stack data structure works. You only have access to that top plate. If you want to get a plate, the only one you can grab is that top one. And if you're going to add more plates to the stack, you're going to add them to the stack one by one on the top, right? And so in this little diagram here, we can see that we've got a stack of elements, right? We can see that the one at the top is the newest and the one at the bottom is the oldest. And if we are to push something, we're going to push it onto the top. And if we're going to pop something, we're going to pop it off the top, right? So this stack idea is something we can very quickly and relatively easily implement on our own using, for instance, an array as the underlying data structure, right? We would have a class called stack. In there, it has an instance variable. It's an array. Let's just say that we're just storing ints right now. So it would be an array of ints. And I would just track which element in the stack is the newest, right? Because the newest, if somebody calls pop, I'm gonna give them back the newest one. And if somebody calls push and they give me something else, I'm gonna add it right after the newest one. And then I'm gonna update my index for which element is the newest, right? So we'd still, in this example, we're still using an array, a traditional array as the underlying data structure, but we leave that private. We don't show that or make that accessible in any way to the user that's using this stack class. The only things that we make public are two methods, and sometimes there's some others, but the two most important are push and pop. And push will take an int and it will add it to the stack, and pop will return an int and it'll return the most recent element in the stack. And so this idea here is kind of what I'm trying to get at with this abstract data structure, this stack. it's an idea about how we allow people to access data, right? So for a stack, the only place somebody can add a new piece of information to our underlying int array is right after the most recent element, wherever that is. And the only piece of data that they can get out of our stack, one at a time, is always the newest piece of information in the list, right? So whichever one was added last. A stack is known as a um, first in, last out data structure, or a last in, first out. Basically, that means that first in, last out, meaning the first plate that goes down on the bottom of that stack, 1, 2, 3, 4, 5, 6, 7, right? The first one at the very bottom, that's going to be the last one that gets out of this stack. The other way around would be last in, first out. It's just a different way of saying the same thing, which means the most recent one on that stack is going to be the first one that gets out, right? This is different than a queue. Same exact kind of idea, but with a queue, much like in real life, getting in line at the, let's say, movie theater to buy a ticket, the first person in that queue is going to be the first person out. It's first in, first out. And the last person into that queue is going to be the last person out. So if I was going to make a diagram of a queue right here, could be the very, very, very similar situation, but the push here would not push to the top, it would push to the bottom, right? We would add people to the back of the list or to the end of the list, or queue in this case, right? So the idea here to remember, and Java provides all these classes for us. Java provides a linked list class, Java provides a Hashmap class, Java provides stacks and queues and all these other data structures, and we can use them very quickly by just creating an object of these pre-existing data structures. But what's interesting, or what's important, is to understand what they're really doing behind the scenes. Because, for instance, if I create an array list and a linked list, two objects in Java, and I just use Java's implementation of those classes, the way that we interact with them is very, very similar, right? We add things to an array list, we add things to a linked list, we remove things from an array list, we remove them from a linked list. Same thing goes for a queue or a stack or a hash map or a tree or try. But what's happening behind the scenes about which piece of data we'll be getting back, and or where the data that we're putting in there will be placed in this data structure changes based on the type of data structure that we're using. And again, the data structures are just defined by the behaviors that we program into it, right? So for instance, with this stack, it's just a simple array, for instance, that I could be using behind the scenes, and I'm just adding things to this array, but I'm keeping track of the most recent element at all times, because if somebody calls pop, I'm going to return the most recent element, and I'm going to move that index down one to now point to the newest element. If somebody calls push, I'm going to add whatever new element they're asking me to add to this data structure right after the newest element. And by doing that, by tracking those indices and programming that kind of behavior, I'm taking a simple, simple fundamental array, and I'm controlling the way we can access it so that it behaves like a stack, right? And that's what I mean by this idea of abstract data structures. It's not necessarily something that just exists like an array, that we're all very comfortable using. An abstract data structure is where we apply logic to control the way that we store and access data. So let's take a look at the linked list first. So the linked list is kind of the most common fundamental abstract data structure that people learn after the array and probably the array list. The linked list is a super classic data structure in computer science, and it's a really neat one. But a linked list is simply a list of objects where each object points to the next object in the list, right? So here in this diagram, we can see that we've got this idea of head, and head is just a variable that will point to the first element in this linked list. And in linked lists, typically we call them nodes. And inside that node, it'll be a node class, and we're going to create one here on our own shortly. Inside this node class, it's typically generic, so that's why you see T data. So the data can be anything. It could be a string, an integer, a car object, whatever you want, could be T data. And then it's got an instance variable of the same type, node, and it's called next, right? So let's say that we're dealing with cars, right? I could say, and I'm going to simplify it way down. I'm going to say car C equals new car, and then imagine inside that car class, there was an instance variable of type car called next. So then I could say, car D equals new car, and I could say C dot next equals D, right? So the first car is literally pointing to the second car. And then I could say car E equals new car, and I could say D dot next equals E, or, and so now C points to D, D points to E, and that can just keep on going forever. And the reason that this is kind of such a fundamental and useful data structure is that if we're like the most useful case is that if we're only adding and removing elements from the front or from the head, the very tip of this linked list, it's incredibly fast, right? Because all we ever have to do is add something to the very front of the list or remove the first element from the list, right? That list could be 3 elements long, or it could be 3,000 elements long. And the time it takes for that operation to complete is fixed, basically. And we're not going to go too big into big O notation today, but some of you may have heard of big O notation, which is definitely worth looking into. And big O notation basically just helps us understand the complexity of our algorithms, or the algorithm, meaning how complex will it be to insert, find, or remove an element from this data structure. If we're adding or removing something from the very front of a linked list, that would be a big O of 1, and 1 just means fixed time, meaning whether there's 3 elements in this list or 3 million elements in this list, the time and complexity it will take to add or remove something from this list is fixed if we're only adding or removing from the very front of the list, right? Let's say we're adding to the end of the list, which is a very, very common behavior with a linked list. Then when we add, that's going to be a big O complexity of n. So it would be O of n, meaning it is complex. It is as complex as the list is long, right? So best case, if you're adding and removing from the very front of a linked list, you've got O of 1. It's fixed time. It's super fast. And worst case for insert, if you're adding to the end of the list, then it's O of n. So it will be as complex as the list is long, meaning because it'll have to iterate over every element till it finds the end and then insert there. And this will make more sense in a moment as we build out a custom linked list. So at its core, as this diagram shows us, a linked list is just a collection of nodes where each node points to another node. And I'm saying the word node very specifically because it's the classes of type node, and it points to another node of the same type, right? So it's just one car that points at another car, that points at another car, that points at another car, and on, right? And that data structure can come in very, very handy. A quick nod here to stacks. Remember how with a stack, we can only add or remove from the top of the stack? So a linked list where we only add and remove the head node or the first node, it lends itself perfectly to be the underlying data structure for a stack, right? So where in my stack class, maybe instead of using an array and tracking the index of the most recent element, instead of that, I would just use a linked list as the underlying data structure. And all I ever do is add to the front of that linked list or remove the element from the front of that linked list. And this is important, right? Because our algorithms that we write, especially when we start to process millions of pieces of data and we start to write really complex code, slight differences and slight tweaks in the logic about how we store, access, manipulate, analyze data can have cascading effects, right? So one algorithm might work really, really well for 10 or 100 elements, but then the moment you try to use that algorithm to sort or store 10 million elements, all of a sudden it breaks down really, really quickly. And by breaks down, I mean it can take 30 seconds or 45 seconds or a minute or whatever to complete in sorting this collection of numbers or in finding and iterating over this data structure appropriately. And obviously, as we all know, in today's modern world, if anything on our computers takes longer than like literally 1 second, it's too long, right? So as programmers, we're always trying to figure out what is the absolute most efficient way that I can, in this case, store and access this data. Linked lists are not necessarily the most efficient data structure for most use cases, right? They lend themselves very, very well to, for instance, a stack. You could also use them for a queue, where in a queue, I would keep track of the tail node, the head node, and the tail node. So I'd always keep track of it as a variable, which node is the very front of this list and which node is the very back of this list. And in a queue, when someone adds an element to the queue, I would add it to the back of the list. And when they pop something from the queue, I would just remove it from the front of this linked list. So it might be a little confusing because we're kind of nesting the idea of data structures here. But the linked list is this super fundamental computer sciencey concept that is really important to understand, because it also helps you understand that you can really do whatever you want with code to structure and understand, store, and access data as you see fit. So we're going to take a look at that in just a moment. I'm going to also jump over to the Hashmap slide here. Just before we get into the code, a hash map is another data structure. It's really, really great. It's got very, very fast access. And a hash map stores key value pairs. And a perfect example of a key value pair, or like a hash map, would be a phone book, right? So a phone book is just a list of names, and for each name, there's a phone number. The name is the key, and the phone number is the value. That's a key value pair. Another example might be, let's say I have a list of countries and their populations, right? So the key would be the name of the country, and the value would be the population. The value does not need to. Keys are typically something simple like a string, like the name of a country or somebody's name, right? But the value can be anything. It can be as simple as a phone number. It could be complex as some really complex object that has a lot of other objects composed within it, right? So the hash map, and we'll get into this, but the hash map, again, underneath the covers, it just uses a fundamental array, a traditional simple array, but we control the way and that we access those elements by running a really, really smart little algorithm over it called the hashing method. So before we get too deep into that, let's go look at the linked list. We're going to build a custom linked list, and then we'll come back and we'll talk further about the hash map. So, all right. So the idea of a linked list, and I'm going to jump right into the code here, might be a little confusing, but hopefully it makes sense as we go on, right? We're also going to use generics, which are a little bit more on the advanced level of Java, but I want to make this a proper linked list right from the get-go. So the way that a linked list works, especially a generic one, is that right here I'm going to say that this is generic, right? So I basically just added what's called a type parameter here. And this basically says that this class is generic. And then inside this class, I'm going to have T data and linked list node next, right? And keep in mind that this class is named linked list node. And now I've created a instance variable called next, right? And let's just go ahead and I'm going to make this data private, and I'll create a little getter and setter here for that. And I'm going to create a couple constructors. I'm going to have two ways that I can create new linked list nodes. One is going to take in, well, let's just start with one. So I'm going to create a constructor. It's called public linked list node. And it's going to take in some T data. And I'm going to say this dot data equal data, right? And if you're not familiar, just a quick refresher on generics. When I create an object of this class, so for instance, I'll just do a quick one right here. Right here, I can say linked list node, and then I'll give it the type, right? So I'm going to say like string equal, call it list equals new linked list node. And technically, this takes a piece of data, so I'm gonna also just do just at least for demonstrative purposes, I'm gonna overload this constructor with just a default one. So notice here when I created an object of this linked list node class, I had to say what the type was, right? And so what this means right here when I say string in the diamond brackets is that everywhere that you see a T in this class, it will be replaced with string, right? So that effectively, when I did that string in diamond brackets, it makes this data string. And then it makes this T a string, it makes this T a string, and it makes this T a string. So now all of my methods will work and interact with strings, right? Get data, set data, et cetera, et cetera. Everywhere that you see a T in this class, it will become a string. And this is called, the technical term for this is called type erasure, right? Where the JVM actually isn't aware of the T. All the JVM is aware of is that the type of this class, anywhere that there's a T, is we want to change that to a string, right? So just a quick primer on how generics work. They're super useful. It allows our classes to be really flexible. So let's start right there. We've got this idea of a linked list node class. It's got this private T data, and it's also got a link to the next node, right? So link list node next. And I think we're just going to start right there. So now I'm going to go over into an actual linked list class. And what we always have to do in a linked list class, or sorry, in any kind of data structure, is that we need to be able to add data. We need to be able to find data, and we need to be able to remove data. And anytime I'm working on a new data structure, it can get pretty complex really quickly, especially as you get into these super complex data structures. And so I always, when I'm starting to work on one, I just remember all I'm really trying to do here is have the ability to add data, find data, and remove data. And I simplify the problem down to that. And then let's just start with the simple idea of adding data, right? So that would be, again, this linked list class is also going to be generic so that I can pass the type straight down through to the linked list node, which will make sense in a moment. And one thing, the most important thing in a linked list is that you always have to keep track of the head node, the first node in that list of nodes, right? Because the first one points to the second one points to the third one points to the fourth one, etc. So if we lose track of that first node, we lose the whole list, right? If we don't have the first one, we don't have any of them, right? And so something that we always do is linked list node of type T head. And this is just an instance variable in this linked list class. I'm gonna make it private. We don't want anyone to have access to that variable. This variable is gonna be used to track at all times what is the first node in this list, right? So when somebody adds data, they're basically going to want to say linked list.add, right? So to me, that is a void method. It's called add, and it takes some T data, right? Because again, we're using T so that this linked list can be used with any type, right? And when I want to add something to this linked list, the first thing that I should probably do is I should say if head equal null, right? If there is no head, if there's no first node, then I would say linked list. I think there's multiple ways to do this, but I'm actually going to do it right here. Linked list node of type T, let's call it node equals new node. And I'm going to pass in pass in data, and this is linked list node. And I would call it just node or something like that, but right now I'm trying to make it super self-explanatory. And so what I've done right here is I've created a node, this linked list node. I've called this constructor where I've set the data, right? I'm just going to pass it the data. I'm going to create this linked list node, and it does not do anything else, right? It just creates this simple node where the data is set upon it, right? So create simple node containing data. Now that I've got that node, and again, right now I'm in the add method, so I'm definitely going to want to be able to add something. Now that I've got that node, I'm going to check to see if the head is null. Is there anything in this list already? If not, meaning if head is null, there's nothing there, I'm going to say head equals node, right? And so this basically is going to say, great, okay, now we've got the node stored in this linked list, and it's currently the head because there are no other elements in this list. And then after I do that, I'm done. I can return. There's nothing else I need to do here. If this is not the case, if head is not null, then what I'm going to do is I need to iterate over this list. And there's, there's two ways that we can do this. We can say add to front or add to back of this list. And so I'll start with add to front and add to front. And if we have time, I'll show you both. So in add to front, what we need to do if the list is not null, and let's see if I can maybe even kind of draw this for you. Where's the, nope, can't get my mouse over there. With a linked list, imagine that we've got the, let's see, pardon me, I'm see if I can, it'll help if I can draw this. Nope. I've got a little stylus, but it only works on one of my monitors right now. So imagine that we've got this linked list, right? We've got elements, and to keep them kind of random, let's say I've got elements D, E, and F, right? And D points to E, E points to F, right? And if I want to add something to the front of this list, I should also point out that head, this variable where we keep track, we're always tracking the most recent, not the most recent, but the first node in this list. Head always points to the first node in this list, and the first node of this list will always point to the other nodes in this list, right? So if I want to add a new element to the front of this list, what I effectively have to do is I have to create that new element, like I've done on line 10 here, linked list node equals new linked list node. I've got to take that new node and I've got to say node.next equals what is currently head, right? So let's go ahead and do that. I'm going to say, oh, wait, I can draw. Node.next equals head. Right? So I've taken this new node, this one that I created right here that has the data, and I'm saying dot next equals whatever one the head currently points to, right? And then I'm going to say head equals node, right? And that's all I have to do. So let's see if I can, I'm going to try this drawing one more time. So let's say that we've got this list here, right? This one points to that one. This one points to that one. This is my little linked list. This is D, E, and F, right? And then I've got this idea of head, which points to the first node at all times. So head currently points here, right? And if I want to insert something, and apologies for this very, very rudimentary drawings here, if I want to insert something into the front of this linked list, and so what I effectively have to do is create this new node, which is what I've done right here on line 10, right? I've created this new node. And then I'm going to say node.next here on line 17, node.next equals head. So head currently points to this. So it's effectively like saying like this, but head points immediately to this one. So what it's actually doing is basically saying node.next equals this one, right? And then head, line 18, equals new node. So we are effectively redirecting what is currently recognized as the front of the list to that new node, right? This is a really, really efficient way to add, for instance, if we were going to use a linked list as the underlying data structure for a stack, this is exactly what I would do. All I ever want to do is add things to the front of the list, and all I ever want to do is remove things from the front of the list, right? So that's about it for the add to front. Let's see if, let's do a quick add to back or add to the end. So this would be public void add to back. Again, I'm going to take in the T data. And I'm going to do the same exact thing that I've done here. So I'm going to create this new node with the data that the user has passed in. I've got this new linked list node. If the head is null, that means there is nothing in this list. So go ahead and set the head to this new node and return. We're done. Now this list contains one element. It's the one we've just added, and it's also the head. If the head is not null, then what we need to do is iterate over the entire linked list until we get to the very end. And so the way that we do that, we never want to put the head of our linked list. We always want to track that head of our linked list. So we don't ever want to use that head variable to iterate over the list. And so what I'm going to do here is I'm going to create a linked list node of type T. I'm going to call it Iterator equals head. So not new head, equals head, right? So now I've got this other variable called Iterator that also points to head, points to the first one. And then I'm going to say while iterator.next does not equal null, iterator equals iterator.next. And this is a simple little thing here, and it's a little bit confusing, but basically what it's doing is it's saying, for instance, while head.next does not equal null, but we don't want to use head, right? Because we don't want to lose that original reference to the beginning of that list. So we created a copy of it called iterator. While iterator.next does not equal null, meaning there is another one, go into this while loop, and iterator equals iterator.next. So we're effectively going to, if I bring back my handy, horrible drawings over here, we've got this, we've got this linked list, and this one is, I'm not going to try to point it, but that's head, right? And we also made a copy of that variable called iterator, or just another one. And so we say, hey, iterator, which is currently this one, is there another one? Yes, there is. Okay, great. Iterator equals iterator.next. And then we say, great, keep looping. Dear iterator, we're currently on this second one right here. Oops. Dear iterator, do you currently have a next element? Like, do you point to something else? Yes, they do. This element does. So we go in there, we say iterator equals iterator.next. So now iterator is on this one, right? And in this case, we say, dear iterator, which is currently the third node, is there a .next? Is .next not equal null? No, .next is null. There's nothing over here. So at that point, we can exit the loop, right? And when we exit the loop, we know for a fact that we're at the end of the loop, right? Or sorry, the end of the list. We know that iterator will point to the last element in this linked list, at which point we can just say iterator.next equals node, which is this node that we created right here. And so that will effectively add an element to the end of the list every single time. So we come into this add to back method, we say linked list node equals new linked list node. We're just setting up this node that we want to insert into this list. And if head is null, head equals node and return. Otherwise, we're going to have to iterate over this list. So we create an iterator. And while iterator.next does not equal null, iterator equals iterator.next. So just keep iterating down this list until .next is null, at which point we know that the current node that we're on, that we're iterating on, that's the last one in this list, at which point we will exit the loop, and at which point we can just say iterator.next equals node, right? So let's jump straight into the remove method, because in the remove method, we also find data that we're looking for. And what we're going to do here is we can choose whether or not we want this remove to return the element. Let's just go ahead and say that we, not for right now. We're just going to keep it simple and remove some element from the list, right? From this linked list. Again, it's going to take in, we're going to pass in the element that we want removed, right? We have to indicate which element we want removed. And so the same thing goes here. While in terms of checking if the head is null, right? If the head is null of this list, then we don't need to do anything. There's nothing to do, right? The head is null, there's nothing to remove. Like that's, we're done here, right? Then we've got three cases, right? The first case is remove from front of list. So imagine that the thing that we're trying to remove is the very first element. We might not know that, but it just so happens that the thing we're trying to remove is the first element in the list. That's one case. The second case is that we're removing something from the middle of the list, which is the most interesting one. And then the third case is we're removing something from the very end of the list. And each of these has slightly different code that we've got to write. So the first way to check it is that we just have to say, is head, is the data at head equal to the data that somebody just passed in? So here I'm just going to say if head dot get data dot equals data, right? And head.getData, this will return the data in the head node. I'm going to check if it equals, using the dot equals method, we'll actually check if the two elements are contain the same data. And what I'm checking against is data, which is this variable, this parameter that was passed into this method. So if head.getData.equals data, that means that the first node contains the data that we want. All I need to say is head equals head.next, which is basically just going to say, pull up some horrible little drawings here. Let's say we've got node 1, node 2, node 3. This is currently, I'll just do an H for head. Head currently points to this first node. If this is the one that we want to delete, right, all we have to do is, because the way that a linked list works, all we have to do is point head to the next node. And now this node has effectively just been cut off. There's nothing that points to it anymore. And the Java garbage collector will come along and it'll garbage collect this object. So if it's the first node that we want to delete, all we have to do is move head, point head to the next node, right? If there's nothing after the first node, let's say we want to delete the first node and there is nothing next, head.next is just null, which sets head to null, right? So that works for us. Let's work on the second case here. So remove something from the middle of the list. So if head.getData.equals data, that means we found it in the, and I guess we can return after this because we're done here. If this doesn't execute, that means we need to iterate. So I'm going to create a linked list node, again, T. I'm going to call it iter, just for short for iterator, equals head, not new head, equals head. Basically just make a copy of this head variable because I don't ever want to modify that head variable. It's like sacred. Don't mess up the head variable and what it points to, because if you lose that head that points to that first node in this linked list, you lose the whole list. There's just no undos. There's no other way around it, right? You got to protect that that head variable that points to the first element in the, the head of the snake, basically, the linked list being the snake. So now I'm basically going to say while iter dot next dot get data, and I'll say not. I'm going to use not, while not iter dot next dot get data dot equals data. Basically what I'm doing is I'm checking what is the data in the next one. Does the next one contain the data that I'm looking for, that I'm actually trying to remove? If not, keep on iterating. So iter equals iter dot next. One other thing I should check here is I should do two things. I should say and iter dot next does not equal null. So I'm basically checking to see, does the next one contain the data that I'm looking for, the data that I'm actually trying to delete? And like while the iter.next is not null, just keep looping, right? The moment the next data, the one in the next data has the data we're looking for, or the next element is null, this while loop will exit, right? So there's two cases after we exit. One is that we've found the data that we're looking for. So here I would say if iter dot next dot equals, I should say iter dot next dot get data dot equals data, then we found it and we need to delete it. So this is where it gets a little bit interesting, but at its core, what we have to do, and I'll give you a horrible little drawing here. I've actually got a stylus and a pen, but for some reason I can't get the stylus to work on this monitor. So it's mouse drawings for here. So let's say that we've got this linked list, right? Get a little more space here. This one points to that one. This one points to that one. And this one right here in the middle is the one that we're trying to delete, right? It's not the first one because we handled the removing something from the beginning of the list here. What we're doing is removing something from the middle of the list. So what we need to do effectively is iter.next So iter.next is, this is the iter, the first one, .next is the second one. What we have to do is we have to point the first one at the third one in this case. And then this remains in the linked list, and then this will just get garbage collected by the Java garbage collector because there's nothing pointing at it, right? So basically what we have to do here is just like bunny hop over the one that we want to delete. So the way that we do that is we say iter.next equals iter, and this is where it gets a little confusing, .next, right? The other case here is I also want to make sure that iter.next does not equal null, right? If iter, like, so if the next one contains the data and there is one after it, I want to do this, right? I could also check this case, right? If iter.next.getData equals data and iter.next.next, I could probably just say else. So if the next does equal null, so if this returns false, right, this if statement will not enter. But what that effectively means is that the next one contains the data that we're looking for, but it's the last one in the list, right? So let's get rid of that. Imagine that we basically iter.next.next, there is no iter. Like, let's just assume that this is our to list and this is the one that we need to delete, right? iter.next.next is null, so that'll be a null pointer exception. So all I have to do here is say iter.next equals null. Iter.next equals null, right? Because iter.next, remember, is the one that contains the data that we're looking for, right? One thing I can do here before I do any of this checking is I can say if not iter dot next dot get data dot equals data. That means we've exited this while loop, right? But the next one does not contain the data that we're looking for, which basically just means that we have not found the data that we're looking for, and we've found the I could say or to keep it simpler here too, I could say if iter.next equal null, meaning we've gotten to the end of the list, and let's do both actually. So this is basically saying if the next one does not contain the data or the next one is null, well, I'm going to overconfuse this here, so I'm just going to skip this. I apologize. Limited time. So if iter.next.getData equals data and iterator.next.next does not equal null, meaning we've found it and there's something on both sides of it, we need to effectively just point the pointer from the first one to the third one in this case. Otherwise, if iter.next.getData equals data, and this is an else if, which would mean that this is false, iter.next.next is null, then all I'm going to do is say iter.next equals null, right? The last, and this basically, just so you know, handles this case, right? Meaning the element that we're looking for is the last element in the list, right? So we can remove something from the front of the list, we can remove something from the middle of the list, and we can remove something from the end of the list, right? So this is a little bit confusing, but let's just see if it works. So I'm going to create a linked list controller. And in here, I'm going to put our main method. I'm going to say linked list, and let's do of type string. And then I'm just going to say list dot add to front Ryan. List dot add to front Kim. List dot add to back Martin, let's say. And just to test this real quick, we should probably create a little method that'll print all the elements of our list. So I'm going to do that right now. So I'm going to say public void print. And I'm going to create a little iterator so I don't mess with my head variable. And in my linked list node class, I'm going to create a little toString. So we'll just say so if the iter is null, meaning there is nothing in this list, go ahead and return. Otherwise, I'm going to use a do while loop. And I'm going to say iter dot, where did I put that? Linked list. While iter does not equal null. Okay, so what I've done here basically is I've created my iterator so I don't mess with my head variable. If the iterator is null, I also could have said here if head is null, they're the same, return. There's nothing to do here. Otherwise, I'm gonna use a little do while loop. And all I'm gonna do is I'm gonna print out that element, that toString. And all I did is it's just gonna print out this linked list node and then the data for each node. And then I'm going to iter equals iter.next. And then I'm going to keep doing that while iter is not null. So over here in my linked list controller, I should be able to say list.print. And I'm expecting to see printed out. So we did add to front Ryan, add to front Kim, add to back Martin. So I'm expecting to see that it prints out. It's going to be on 3 lines, but Kim, Ryan, and Martin in that order. And let's see. Fingers crossed. Just compiling here. Cool. So it's not the prettiest looking thing, but you can see that it printed out the node Kim, the node Ryan, and the node Martin. And so let's just keep on testing that. I'm going to say list.add to back. Let's go with Gilad. And then list.add to front Brandon. And list dot, I'm just really testing it here, add to front Evina, and then print. So basically, now I'm expecting to see Evina, Brandon, Kim, Ryan, Martin, Gilad, Brandon printed. It's just because I said add to front, add to front, add to back to back. It's a little funky, but just demonstrating that both the add to front and the add to back are working. So we should see Evina, Brandon, Kim, Ryan, Martin, Gilad. Right. Evina, Brandon, Kim, Ryan, Martin, Gilad. So now let's test removing some things. So the first thing I'm going to test is list.remove Ryan. And then I'm going to do a list.print. And so now we should see the same exact list printed, but Ryan missing from the beginning, or sorry, from the middle. And instead of printing it twice, I'm just going to print it once. I could do a little. Cool. So in the first list, Ryan's there in the middle, and in the second list, Ryan is not. Let's, so that was one from the middle. I actually want to demonstrate removing from the front. So list.remove Evina is all the way at the top. And then I'm going to remove the one at the very end, which is Gilad. All right, let's see if this works. Uh-oh, null pointer exception on line 56. While iter.get, so this is after the first print. So while iter.next, null pointer exception. Well, iter.next.getData.equal, well, not iter.next.getData.equals null, and iter.next does not equal null. Iter equals iter.next. So, oh, you know why? Avena has a capital E. So that's a bug I just found there, right? When which I should fix. And today in this webinar, we don't necessarily have time to put in all the bells and whistles and the silver lining. But what I just discovered there is that in the list, I added Avena with a capital E and Brandon with a capital B. So just just to keep everything conventional, because it got all the way to the end of the list without finding Avena, and then I've got a bug there that I would need to resolve. But let's just see if we can get this to work as is right now. Okay, so first we've got everybody, and then we remove Avena from the front of the list, which is correct. She's no longer there. And then we remove Ryan. So Ryan's in the second list set, but not in the third, which looks good. And then we remove Galad, which is in the third list there, but not in the final list. So looks like our linked list is working just as expected. We can add things to the front. We can remove things from the front, the middle, or the back. And we can keep adding and adding and adding and adding and adding. And you know, that's really it. There's more that we can add here. We can add like a .contains method. I needed to do some debugging on my null pointer exception there. I'm not exactly sure what happened. But the linked list is basically this simple node that has the idea of some data. It's a generic. It can be whatever we want. For instance, linked list of type string. And all it does is hold a little bit of data, and then it links to another one that we call next. And by another one, I mean another node of the same type, right? Then in my linked list class, I've got, here we've just done the add and remove methods. But in the add, I've got two strategies. I've got the ability to add to the front of this list, in which case all I ever do is say, if head equal null, then head is new node, meaning that it was an empty list, so just add it. Otherwise, with this new node that we've just created with the new data that somebody's trying to insert, trying to add, we say this node.next equals head. So point this new node to the front of the list, and then point head to this new node, right? The other way is to add to the back of the list. So again, I create this node that contains the data that the person wants to add. If the head is null, that means there's no list right now. So just go ahead and say head equals new node. So now this is a list of size 1 and return, we're done. Then we need to iterate over the list, and we create an iterator so that we never actually modify that head variable. Like I wouldn't want to say head equals head.next right here, because then we would lose, you know, that first or second or third element in the list, because as soon as head no longer points at that first one is gone, you know. So we have to maintain the sanctity of that head variable. So I use while iterator.next is not equal null, iterator equals iterator.next. So this is going to iterate us from one element in this list to the next. As soon as iterator.next is null, as soon as this comes back to false, right, iterator.next is null, I know that iterator is the last node in this list, so I can just say iterator.next equals node. And then in the remove method, we've got three strategies. Again, we check to see if the list is empty, in which case we just return. We check to see if the first element in the list is the one we want to delete, in which case we just say head equals head.next, which effectively deletes that first node. Otherwise, we need to remove something through the middle of the list, which is what we're going to iterate over the list. And so while the next one does not contain the data we're looking for, and the next one is not null, iterate. Iterator equals iter.next. As soon as we leave this while loop, we know that the next one either contains the one we're looking for, or the next one is null, right? If the next one contains the data that we're looking for, and the next one is not null, then we do this interesting iter equals iter.next.next, right? But we don't want to do iter.next.next if this is null, right? If next is null, that's basically like saying iter.null.null. That's a null pointer exception right there. And that's where our bug is that we determined. But this is effectively like if I had the list 1, 2, 3, and I'm trying to delete 2, right? I say iter, which is 1.next, which is currently 2.next, which is currently 3. So iter.next equals now points to 3. Iterator.next equals iterator.next.next. So point bunny hop over the 2. 1 now points to 3. If we get the other case is that we got out of this while loop, not because we found the data that we're looking for. Well, it's quite possible that the data is not there, in which case nothing will happen. But it's quite possible that iterator.next.next is null, meaning the one that we're trying to delete is actually the last one in the list. Like in our list of 1, 2, 3, it's the 3 that we're trying to delete. So therefore, when my iter is on 2, and I can do iterator.next points to 3, iterator.next.next points to nothing. So all I have to say is iterator.next is null. 2.next is null. Drop the 3, right? So quick, there's more that we can do here in the linked list. There's several more methods that we can add, contains, find, and a few others. But this is the general idea of a linked list. This took a bit longer than expected. We are actually at the 1 hour mark right now. But luckily, we're gonna jump really quickly into the hash map, which I think we can describe relatively quickly. So just as a reminder, the hash map, this is all a bit confusing here, but a hash map stores key value pairs, right? And there's this really interesting function that we run on the key to determine where to store the data, right? So let's jump straight into that and take a look. In my same kind of deal as we had with the linked list node, I'm gonna have this hash map node is going to be generic, but it's going to take 2 types, K and V. And keep in mind that these generic types, these letters could be anything. They really can be. They don't have to be K or V. K or V is just the convention because of key and value. T is very often used for type. So I'm going to say K key and V value. And then this is where it gets interesting. Hash map node KV next, which should look a little bit familiar. And for right now, I'm just going to leave this super simple. I'm going to keep all of these, in their default access modifier. But what happens with hash maps is that we have collisions from time to time, which is going to make sense in a moment. And when we have a collision, what we actually do is we insert the new node into this hash map as a linked list, which will make sense in a minute. So let's go ahead and jump over. We're going to leave this class just as it is for right now. Let's go jump over to our Hashmap class. This Hashmap class, again, is going to be generic. It's going to take the same 2 types, K, V for key value. And what this Hashmap is going to do is I'm going to have a private array of Hashmap nodes. And I just put this KV everywhere. Let's call it data. And again, I want this private because I don't want anyone to have direct access to this at all, right? Again, we have the idea of adding data, and let's just keep it simple, removing data. So add, let's just start from the top, public, void, add, and then this is going to take in a key, and a V value. And remember, when I create an object of this hash map, I'm going to indicate the 2 types that I want this hash map to store. So it could be like, let's say I was doing countries and populations. The type, it would be, let's make this my hash map, or just so it's obvious that this is our hash map that we're using. When I say my hash map, map equals new my hash map, I'm going to give it inside the diamond brackets 2 types, string, comma, integer. String being the name of the country, integer being the number of people that live there. So great. So I've got my add method. And in a hash map, it's oftentimes put. So let's call it put. We're going to put something in a hash map. So the first thing I need to do here is, and this is where hash maps are so cool, right? What I'm going to do is I'm going to find the hash for, sorry, I forgot something. This actually needs to be an array. And we're going to start with this array. It's going to be an array of hash map nodes, right? Just the square brackets. Looks a little confusing, but it's just an array of hash map nodes that happen to be generic. And I'm going to start with this length of 10. And what I'm going to do right away is I'm going to get the index. Let's call it get hash. This is a little method that we haven't written yet, so I'm going to create this method. And inside the get hash, we're going to do, this is where the magic of the hash map happens. So I'm going to say int index equals math.absolute. And all this does is means I want a positive number, absolute value. I don't want a negative number. And then I'm gonna this is gonna take in a key, k key as an argument. I'm gonna say key dot hashcode mod data dot length and return index. So let's take a second just to sit on this. This is really, really cool here. This is the magic of the hash map, right? So the hashcode method, this exists in the object class of Java. I'll just drill down onto it, and I'll just look at the Java doc real quick. Returns a hashcode value for this object. The method is supported for the benefit of hash tables. The hash code for this object, let's see here. Whenever it is invoked on the same object more than once during an execution of the Java application, the hashcode method must consistently return the same integer, provided no information used in the equals comparisons on the object is modified. So effectively what that's saying is, if I call, let's say, I can just do this real quick. For int I equal 0, I less than 10, I plus plus, sout. Right, so I'm not actually gonna run this right now, but if I were to run this, if I run the hashcode method, and the hashcode method exists in the object class, so that means every single object in Java has access to this method, because the object class is like the grandparent class of all classes in Java. Every single object in Java has access to this hashcode method. If I call hashcode on the string Ryan 10 times, it's gonna print out the same exact integer every single time, right? So let's just assume that what it prints out is this number, right? And it is gonna look something like that. It's a big old number. And with that number, I wanna make sure I get a positive number. There's a half chance that the hash code could come back as a negative number. So I'm gonna say math.abs key.hashcode. So let's say the key is Ryan. Let's say it was names and phone numbers. So the name, Ryan is the key. I'm gonna get the hash code on that, which returns this big random number. And then I'm gonna use the modulus operator. And you'll remember this from day one of this webinar, or if you've already been doing some studying. The modulus operator will return the remainder from division. So that number, mod 10, equals 1, right? And that 1, that's the index where I want to insert this new node with the key Ryan and the value like my phone number. What's interesting and really, really brilliant about this is that no matter what this number is, like it has to be, for instance, let's say it has to be between like 0 and 9 right here, right? Otherwise it just goes back up to 8, 0, 9, then it goes to 9, 0, 9, right? This final number is guaranteed to be a number between 0 and the value that we're modding by. This value is the length of our array, right? So what that means is that this result is always going to be a valid index, right? There's no number, no matter how big or how small, when you mod it by 10, that will not give a result between 0 and 9 inclusively. Does that make sense? Like the remainder of something divided by 10 can't be 10, right? Because otherwise the remainder would be 0, because 10 would go into that number one more time, right? So let's just, this mod 10 would be 0. This mod 10 would be 1. This mod 10 would be 2. This mod 10 would be 3, 4, 5, 6, 7, onward, all the way to 9. Mod 10, the remainder would be 9. When we go back up to 0, the remainder is 0, right? So this is really, really brilliant, because this index now will just hash this key for us, and it'll give us some index. So let's say that the hash was this big number that ends in a 4. Mod 10 is 4. So I'm going to return 4. And then that is the index where I'm going to insert this new element, or where I'm going to find this new element, right? So and why this is so interesting and so intelligent and so smart and just like cool, is that the only other way to find something in an array, let's say that we have an array of size 10, right? And I need to see if the element Ryan is in there. It's an array of strings, and I need to see if the string Ryan is in there. The only way that I can do that, there is no other way around this. The only way I can do that on a traditional array is I start at the 0 index. I see if it contains Ryan. If it doesn't, I check the first index. Check, nope. Second index, nope. Third index, nope. fourth index. Sure, there it is. But the worst case scenario is that I would have to check every single element in that array because it's equally as likely that Ryan would be at the end as it is the beginning. So to find something in an array, the only way that we can do that, like logically, traditionally, is to start at the beginning of the array and check every element in that array until we find it or until we reach the end. If we found it, sure, we found it. If we reach the end and we haven't found it, it's not there, right? That, as far as big O complexity goes, is an O of n, right? It's as complex as the list is long. What's interesting here when we use this hash function is that I immediately can figure out what index I want to insert this element into, or when I'm searching for something, I can do the same exact hash code function. Let's say I'm searching for Ryan's phone number, and we'll do this in a second. So I'll say hashmap.get, and I pass in the key Ryan. Again, I can run the hash function on that Ryan, and it's going to take me straight to index 4, which is where my element is. There was no iteration whatsoever over that underlying array, right? So let's just continue this for a minute, and bear with me. I know we've gone a little over time, but I'll just try to wrap it up here in the next few minutes. So now I'm going to basically say if data at index, this index is just what we got back from that hashcode method, get hash, equal null. So if there's nothing there, nice and simple, then we say data at index equals new link hash map node. And I want to go ahead and create a constructor for this that takes in the key and the value, equals new hash map node. And I'm going to give it the key and the value. And I'm going to go ahead and, ooh, I want that to be lowercase. Right? So if there's nothing at that index, let's say that long string I hashed Ryan, it came out to this really long string of numbers. I mod that by the length of my array. My array right now is 10, right? So I mod that big long number by 10. No matter what, I'm going to get a result between 0 and 9 inclusive. And that result is the index where I should insert this new node, right, in this underlying array. So if there's nothing at that index, my array is called data, and if there's nothing there, then I'm going to say data at that index, so array at the index, let's say 4 in this example, equals new hash map node, and these diamond brackets are optional. And then I'm going to pass in the key and the value, right? And I'm going to return, because we're done there. If data at index is null, this is where it gets a little bit interesting. Then we basically have to create a hash map node. So I'm going to say hash map node of type KV, and I'm going to call it iter, a little redundant, a little familiar here, equals data at index, right? So basically we're saying, give me that hash map node that's already there, because, so here's where it gets interesting. What we're talking about now is conflicts, right? So let's say that Ryan hashes to, oops. Let's say that Ryan hashes to this number, and then let's say that Kim hashes to, oops, that number. Totally different numbers, right? But when they mod by 10, they both get 4, because this number, mod 10, is 4, right? This is expected. This is called a collision. And there's just really nothing we can do about it, right? Other than plan for them. So what we're doing up here is we're planning for the collision. So here we're basically saying that there is already something there. Let's say we've already inserted that Ryan node, and now we're trying to insert that Kim node. And the hashes both, they both come back to 4. So then what we do is we add Kim as a new node in a linked list at that index, which is where it gets a little bit interesting. But so here I'm going to say hashmap node kv iter equals data at index. And then I basically iterate over that linked list while iter dot next does not equal null. Iter equals iter dot next. As soon as iter dot next is null, that means we've reached the end of the list. So I can say iter dot next equals basically the same code right here. New hash map node, right? So imagine that we've got that array of length 10, and we inserted, Ryan and my phone number first, and so that went into node. We created a new Hashmap node, and we put it at the index of 4 of this array. Then we tried to insert Kim and her phone number, but Kim and Ryan, the keys, they both hash to a number that ends in 4. Therefore, when they mod by 10, they're both going to get the number 4 as the result. Therefore, both of our Hashmap nodes are supposed to go at index 4. That's okay. That's fine. What we're going to do is we're going to add Kim as a new linked list node after Ryan, which is exactly what's happening right here, which is why it's important to understand linked list before you can really go into hash maps, right? And that's it. That's the insert method of a hash map. So now I want to do a quick, really quickly, I'm going to write one more method. Let's do get data, right? So I want to get data, which is typically what, you don't open a phone book just to look at stuff. You open a phone book to get someone's phone number, right? So this is going to be public v get, and it takes in a k key, right? So for a given key, like I'm going to say hashmap.get Ryan, and it's going to return a phone number, for instance. So the first thing I got to say is, let's see that index. Int index equals get hash, which is that little method that we wrote, and pass the key, right? So whatever it is, in this case, if I'm passing in Ryan, and in our example, it's going to bring back the index of 4. So the first thing I'm going to say is if data, which is my array, at that index is null, that means that there is nothing here. Let's say that I said hashmap.get Jim, and there is no Jim in there, right? So we hash Jim, it comes to the index of 6. We check the array, there is nothing at the index of 6. That means there's nothing there. So here I'm just going to say return null. Return, there's nothing to return, right? Otherwise, if data at that index dot key dot equals key, so a little funny there, but basically I'm saying in this array at that index, so data at the index of 6, that's going to return an element, that's whatever's there. It's going to return a hash map node. Immediately I can call the dot key, I can access the key variable on that element at that index, and I can see if it equals this key that was passed in to this method, right? So if it does, then I'm going to return data at index dot value, right? One other case, if the data at index is null, that means there's nothing there. The data at index has the key that we're looking for. Let's say that we were looking for Ryan, right? It's going to return my phone number. But let's say that we're looking for Kim, and Kim is in that linked list node after Ryan. So if we get all the way to this point, meaning we have not hit this return statement and we have not hit this return statement, then I've got to iterate. So I'm going to say hashmap node kb. I'm generic safe. I'm going to call it iter equals data at index. That, give me that element that's at that index of 4, right? So in this case, that iter would have the key of Ryan and the value of my phone number. And I'm going to say while iter dot next dot key, or how about while, there's a couple ways we can do this. While iter dot next, well, how about while iter dot key does not dot equals key. So I'm going to create this iterator, and I'm going to say, while this iterator's key is not equal to the one that was passed in. So this iterator's key is Ryan. I'm looking for Kim. So I'm going to say iter equals iter dot next. So that's just going to iterate my little iterator from the Ryan node over to the Kim node, right? And then when I exit this loop, and I could also say like, and iter not equal null, right? So if iter becomes null, exit, right? And then I could say if iter does not equal null, that means that we've exited this while loop and we've found the element that we're looking for. We've found the current iterator has the key that we're looking for. So then I'm going to say return iter.value. So let's test this out. I've got an error here somewhere. Where is that? And then we'll say, how about just else return null? Because it is quite possible that you're searching a hash map for something that doesn't exist, right? So I'm going to go create a little Hashmap controller. In here, I'm going to put a main method. I know we've gone a good bit over our time limit here, so I apologize. I want to share this stuff with you. So I'm going to say my hash map, and let's do what we were talking about, like countries and or let's do names and phone numbers. So this is going to be the names are strings, doesn't need quotes, string, and the phone numbers are we'll do them. If the dash is in a phone number, like 415-676 that actually makes it a string. So I'm just going to do phone numbers without any dashes. So I'm going to say string, comma, integer. One thing to note with generic types is that you cannot use primitive types as a generic. So this is not okay. Like you can't do string, comma, int. You have to use the object type, which in this case is integer, and all the primitive types have an object type of themselves. Equals new my hash map. And then I'm going to say, I need a name. Let's call it map. Then I'm just going to say map dot put Ryan and 555 1 2 3 4 5 6 7 8. Integer number too large. Okay, so let's go with long. Kind of funny there, but and then let's do another one. Map dot put Kim 555. Is that a number? One more. And we'll do one more. Map dot put Avina. Right, so now I've put these three elements in this map, right? Basically to test it, I can basically say sout map.get Ryan, and then I'm going to do the same thing for Kim and Ivina. And if everything works, we should see these three numbers printed out in this exact order. Something is not right. So map.get, return null, return data at index. If iter does not equal null, return null. I've got some kind of looping error here. 3515572. Is that ever even used anywhere? Where is that printing from? Because it is printing out my number, and then Kim's number, and then Avina's number. Where are these other ones coming from? So just make sure I'm not just missing something here. Let's go ahead and just make these strings. So it's just going to be string, string. Fingers crossed. Weird. Okay, you're getting some real life debugging. Where is all of this printing coming from? Because I'm not looping here. System.out.println map.get Ryan. Int index equals get hash. Am I printing out? Oh, that's why. So I forgot to comment this out, but this is the hash code for Ryan every time. So every time I'm calling get hash, it's printing out my hash code. So the hash code for Ryan is 3515572. So this is actually a perfect example of how the Hashcode method will always return the same integer for a given key. We just got very, very, very good confirmation of that. So I'm going to go ahead and delete that. And let's try that, run that again. That looks a lot better. And this now, these could have been strings or, or longs, but now that they are actual strings, I'm going to go ahead and format them the way that makes me comfortable. Right, so now we've got this map where we can put in values, key value pairs like Ryan and a phone number, Kim and a phone number, Aveen and a phone number, and then we can access those elements using the key. And what's so great about a hash map, right, is that the best case scenario is that is O of 1 is how we write this, big O complexity, because the time it takes to actually insert something or find something, like when I say, when I use the get method, right here, when I say my hashmap.get, I run this little hashcode method. I called it get hash. That returns an index. That index is going to tell me exactly where that element is. Doesn't matter if this underlying array is 10 elements long or 10 million elements long. This index, because if it's 10 million elements long, then I would just mod in this get hash. Notice how we're modding by data.length. So data.length, if it's 10 million, sure, I'll get some index between 0 and 9,999,999. And that's going to be the exact index where I can find that element, or where it might not be that first one because there might be a linked list there due to collisions. And we're not going to do it here in this call, but the way that we minimize collisions is that we always track the number of elements in our list. So let's say I start with an underlying array of size 10. And every time I add something, I have like a little counter where I say num elements plus plus after every successful add, and maybe definitely num elements minus minus after every successful remove. And let's say that I've got 7 elements in my underlying array in this hash map. I would then, at that point, now that I'm 70% or more full, I would actually resize the underlying hash map. And the way that you would do that is just create a new array of size 20. I would just double the current size. And then for each element in that underlying array, I would call my own put method, and I would pass the key and the value, because with that new array size, the mod operation is going to potentially change the resulting index. So resizing of a hash map is very important, because if you don't resize, the worst case scenario is O of n, because what that means is that you've effectively, let's say that in this hash map, we started with a length of 1, right? This would work. It would work perfectly fine. But what we would end up with is just one long linked list, right? That we put a bunch of random logic around for no good reason, right? So if you're not resizing your hash map appropriately, you'll get a lot of collisions. Let's say that we added 10 million elements into a hash map, but in that hash map, the underlying array is only of size 10. We basically can guarantee that we're going to have 10 linked lists, all with a length of 1 million, which means we're going to have to iterate 1 million times potentially to find the one that we're looking for in there, which is not efficient, right? So that's where that O of n meaning it is as complex as the list is long, is the worst case. So the way that we avoid this is by avoid too many collisions. Collision, 2 L's, by properly resizing underlying array as it fills up, right? Because the more elements we add into an array of size 10, right? The first element, very low, 0 chance of a collision. Second element, low chance. Third element, slightly higher chance. Fourth element, slightly higher chance. Fifth element, slightly higher chance of a collision. Sixth element, slightly higher. Seventh element, we're probably having a collision. Ninth or 10th, 8th, 9th, or 10th element, we're almost certainly going to have a collision, because when we mod that, there's already probably going to be something at that index. And so that's fine. We're having a few collisions and having a short linked list at every index is not bad, because the speed that we can iterate over 3 linked list nodes, for instance, is very fast. But we want to keep it to a minimal number of collisions so that our hash map stays as efficient as possible. You could also there's other methods that you could have in here too, like a contains method. So I could, instead of saying map.getGym, right, I could say if map.contains gym, map.getGym or something. So I could check to see, does this map contain an entry for the key gym? If not, don't do anything. If so, Sure, give me Jim's phone number. Yeah, and you can add all whatever methods you want, right, to make this as useful as possible. So um, when, I've been talking a while here, and I know I've covered a lot of really complex stuff, but I really hope that this starts to demystify, especially maybe as you rewatch this video and look through. We've got some great curriculum on this. There's all kinds of great stuff on the web and YouTube videos, but understanding how these data structures are working, like quite literally, under the covers, under the hood, so that you could rewrite them yourself, is really important. And it also, it's neat because once you fully get it, you could make any kind of data structure you want, right? There's a lot of very common ones like linked lists and stacks and queues and hash maps and stuff, but you could come up with your own. A tree, basically, just so you know, is just a linked list, but instead of each node pointing to the next, in a tree, each node has a left child and a right child. And so that makes a tree, right? And you could make a star data structure or a supernova data structure. You can make whatever you want because you can just define whatever rules you want to control how people add, remove, and find data in this collection of data that you're managing, which is why we call them abstract data structures, because you get to define how they work. So let's go ahead and I'll stop talking here and let's just finish out these last couple of slides. We also, like I mentioned, present. So hopefully this makes a little more sense now, this very complex drawing. Here, key value pairs, I've got names and phone numbers. If I say hashmap.put Jim and the phone number, then I'll say Jim.hashcode, let's say it comes back with 77883. I would mod that 77883 by the length of this array, which is 5, which is going to give me the result of 3. So that's where I'm going to put this new node that contains the key Jim and the value of this phone number, right? And it's really nifty and really great. I really like the hash code. Super fast, super valuable. We can use them on a day-to-day basis. The hash map is a day-to-day data structure that we use coding. The linked list is a little more kind of academic, right? So let's take a look. Interested in learning more? As I've mentioned before, please check out our YouTube. We're adding stuff on there on a weekly basis, and definitely trying to up our YouTube game to help all you out with as many free videos and trainings and tutorials as possible. Please also check out our platform, our learning platform, platform.codingnomads.co. Bunch of great courses on there: Java, Python, data science, web development, JavaScript, Spring Framework, APIs, databases, all kinds of really cool stuff on there. So definitely go check out platform.codingnomads.co. And thank you very much for joining. I hope you've been able to gather some good insight from these 3 days. Day 1, beginning and fundamentals. Day 2, principles of object-oriented programming. Day 3, getting into the more complex data structures like linked lists and hash maps. It's all really great stuff, and I can 100% guarantee you that if you're putting in the time to study this stuff and to get good at this stuff, you will be better for it, right? You will be able to get better jobs, work on more interesting, complex projects, get paid better. It's just a good thing. So I congratulate you for putting in the time to study this stuff and to learn this stuff. And if there's anything that we can do to help you on your path, please feel free to reach out directly. All right, everybody. Thank you for joining. Thank you for sending the questions. Thank you for everything and for joining us here at Coding Nomads. And like I said, if there's anything that we can help, anything that we can do to help you in your path learning, specifically Java and Python is what we focus on, please feel free to reach out, and have a great day.
Hey everyone, thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.